Most drivers assume regenerative braking is a simple mechanical reversal. You take your foot off the pedal, the motor spins backward, and kinetic energy flows effortlessly into the battery. But in practice, this energy flow hits a hard limit at the battery management system. Regenerative braking systems do not provide a limitless passive energy source. When engaged, they introduce a high-voltage power surge directly into the EV powertrain that the system must actively manage. To successfully capture and store this power, the vehicle has to navigate a strict sequence of structural and chemical bottlenecks in milliseconds. The first limitation is purely physical. The vehicle's mass and the laws of kinematics dictate exactly how much energy is even available to harvest. The second gate is algorithmic. The onboard logic controllers must continuously calculate the exact split between electrical resistance and traditional mechanical friction. And the final, most restrictive gate is the delicate electrochemical boundary of the lithium-ion battery pack itself. To evaluate the true efficiency of an electric vehicle, we have to reverse engineer this complete architecture. Extracting regenerative energy requires a high-stakes calculation. The system must maximize recovery while avoiding mechanical failure or irreversible cell degradation. The absolute ceiling for energy recovery starts with the kinematic equation. The raw energy available is entirely dictated by the speed and mass of the object in motion. Consider the math for a lightweight vehicle. A 100-kilogram electric scooter traveling at 30 kilometers per hour outputs exactly 3,400 joules of kinetic energy when it stops. Now look at the battery's limiting factor, the C rate. High-performance lithium-ion batteries safely accept a charge at a maximum rate of 1 C, meaning they require a full hour to absorb a complete charge. To safely absorb those 3,400 joules without exceeding that 1 C threshold, the braking event would have to be dragged out over a full 14 seconds. In reality, a typical stop takes about 2 seconds. The battery physically cannot accept the current fast enough to match the rate of deceleration. For a lightweight scooter, this yields a negligible range recovery of less than 2%. The system generates almost no practical benefit. But when you scale the mass to a 2,000-kilogram electric vehicle equipped with a massive battery pack, the variables change. The larger cell capacity can absorb much higher raw current, allowing an EV to recover 8 to 25% of its driving range. While this massive influx of kinetic energy solves the capture problem, it introduces a complex mechanical control issue. The physics of mass dictate that meaningful energy recovery only works in heavy vehicles. But capturing that force requires the vehicle's computer to actively override the standard hydraulic braking system. Despite the vast energy potential in a heavy EV, the motor's counter-electromotive force, the resistance creating the electrical charge, cannot generate enough torque to safely halt a 2-ton vehicle on its own. To stop safely, the vehicle utilizes brake blending. The onboard controller continuously computes an exact split between the electric motor's resistance and the friction brakes. This chart models parallel braking. Here, the solid orange regenerative line and dotted friction line rise simultaneously. The controller applies both mechanical and electrical braking forces at the exact same time. Applying both systems simultaneously guarantees mechanical safety and is computationally simple, but it leaves recoverable kinetic energy on the table. This graph shows the series braking strategy. The solid orange regenerative line maximizes before the dotted friction line begins. The controller demands full regenerative torque capacity first, delaying mechanical brakes. The friction brakes act strictly as a secondary supplement, engaging only when the absolute torque demand outpaces what the electric motor can physically handle. Running this strategy is computationally intense. The system must perform sub-millisecond calculations of the tire ground adhesion coefficients to prevent axle lock or wheel slip before the friction brakes are triggered. On paper, the series algorithm perfectly optimizes kinetic energy capture, but it relies entirely on a single critical assumption, that the battery is chemically prepared to absorb a massive instantaneous charge. Beyond the logic controllers sits the battery cell itself, monitored by the battery management system, the final uncompromising gatekeeper. Regenerative braking does offer a baseline chemical benefit. By recycling recovered energy back into the system, the battery experiences a shallower overall depth of discharge, which generally extends its operating lifespan. But there is a severe risk. Prolonged, high-intensity reverse currents, like those generated by aggressive series braking algorithms, are a primary driver of rapid cell deterioration. This specific failure mode is known as lithium plating, and it triggers almost immediately when a battery is too cold or already sitting at a high state of charge. Under these conditions, the chemical process of ion intercalation simply cannot keep up with the massive flow of electrons forced into the cell by the braking motor. As a result, metallic lithium permanently coats the anode structure, destroying the cell's capacity to hold a charge. This flowchart details the system's defense mechanism, state of health and state of charge prediction modeling. The path traces directly toward adaptive and experimental algorithms. The BMS uses complex mathematics, like extended common filters and neural networks, to continuously estimate the hidden chemical state of the battery in real time. It requires support vector algorithms and probabilistic methods to process this data instantly. The BMS uses these real-time estimates to enforce a strict ceiling on current intake. If the battery is vulnerable, the system rejects the kinetic energy and shifts the braking load back to the friction pads. The delicate chemical limits of the battery force the entire vehicle to dynamically reject free energy, passing the braking burden back to the physical hardware in a fraction of a second. Regenerative braking is a continuous sub-millisecond negotiation across 3 engineering domains: physics, algorithms, and electrochemistry. The logic flows from the tire's adhesion coefficient into the calculations of the series controller and is finally gated by the state of health filter protecting the battery. But successfully routing the majority of a vehicle's brake energy through this electrical pathway creates a unique mechanical paradox. Because hydraulic friction brakes are relegated to high-torque backups or battery failsafes, they suffer from extreme underuse. Without regular heat and friction to clean the metal, environmental contaminants and severe rust quickly build up on the physical discs and caliper slider pins, leading to uneven pad wear. This dynamic completely flips traditional automotive wear patterns. Instead of wearing out from constant friction, EV brakes fail from a lack of it, introducing entirely new failure modes for modern vehicle maintenance. Long-term vehicle efficiency relies on the dynamic restriction of energy flow to preserve the structural and chemical integrity of the total system.